Okay, so in the last chapter we learned about polynomials, how to factor those polynomials, and how to use that factoring to solve polynomials. In this chapter, we're going to be taking polynomials and putting them into fractions. And so the numerator and the denominator are two separate polynomials, and we do some stuff with that. These are known as rational expressions. So a rational expression is any expression that can be written as a quotient of two polynomials. So this first one, 7 over 3, remember a single digit can be considered a polynomial, so this is a rational expression right here. Other rational expressions are stuff that it's a little bit weirder, so we have a single digit up top and a polynomial on the bottom. Even more, we have a polynomial on top and a polynomial on the bottom. So those are all examples of rational expressions. So one thing that we're going to keep in mind as we go through these chapters is the restriction, what we call the restriction of replacement values. So this kind of comes to light by the fact that we can never divide by 0, right? And so, you know, if we have something like 5 over 0, this is a big no-no. We cannot ever do that. And so what we're talking about by restricted values in these rational expressions is just any value that's going to make this situation happen where we have a 0 in the denominator. So for example, this first polynomial, if my x were equal to a positive 10 down there, then I'd have a 0 in the denominator, and that's no good. So if I wanted to know the restricted values for this one, I can just list them like this. X cannot equal 10. And that's it. That's my list of restricted values for this particular polynomial. For this guy down here, we would have to find the zeros of the denominator to find its restricted values. So we do that by just factoring it. X plus 4. This factors into, let's see now, negative 5 and a positive 2. Okay, and so for this one, if we ask for restricted values, we would solve these two factors for 0. And so we say, okay, if x minus 5 equals 0, then x has got to equal a positive 5, and the same thing with this one here. If x plus 2 is equal to 0, then x must equal negative 2. So our restricted values are these guys that we just solved for down here. So we say restricted values, x cannot equal negative 2, and x cannot equal 5. All right, and so that's how we find restricted values. We just say, well, what values are going to cause us to break a bunch of rules? If we can't see those values in our first step, then we have to factor to figure out what those values are going to be. And so even though, like, you know, we're not going to talk too much about restricted values in these next two sections, after that there's going to be a lot more of them all over the place. So don't forget this concept, even though we might not talk about it too much in the next couple of chapters. I think there's a couple homework problems on it, though. All right. So what do we mean by simplifying a rational expression? Simplifying a rational expression is just like simplifying a common fraction. All we do is we break that fraction up into its factored parts, and then we cancel like factors in the numerator and the denominator. So here's an example of how we do this with common fractions. Right here we have 40 over 60. We can break 40 up into its prime components. So we have 4 times 2 times 5. If we break 60 up into its prime factorization, we get 6 times 2 times 5. So to simplify this, we just cancel like factors on the top and the bottom, and then we write what's left. So the same thing is true with rational expressions, right? Just like with 40 and 60, I have something on the top and something on the bottom. What I want to do is break that up into its factored form and see if anything cancels. And that's it. That's how we simplify. It's just like with a regular fraction. So with this guy, I went ahead and did the factorization right off the bat. You can factor this x squared minus 2x minus 15 into what I have in the numerator here. And then you can factor what's in the denominator into this guy, right? And so you factor them both to see if they have any common factors. This one happens to have 2 common factors, so we'll cross those out. And just like this one up here, we're just going to write what's left. X minus 5 over x minus 1. All right, so when it comes to simplification, make sure you factor it all out completely, see if there's any matching factors and cancel them. That's it. When it comes to simplification, that's all. If you forget how to do that, just remember, what would I do in the common example? What would I do first? Break it all up, of course. All right, so let's do some examples of these. So suppose they ask me to simplify each rational expression here. We've already done something like this before, right? We know that we're just going to take this sort of one step at a time. We're going to consider 8 over 24 and x squared over x. When it comes to the 8 over 24, that splits up into 1/3, right? 1/3. And then the x squared over x, we get to cancel one factor of x in each, and then we get x left. So 1/3 x is what we do when we simplify that. So with example 2, here's another little kind of, this is another example of how they like to mess with you a little bit. We can't really factor too much on the bottom, so what we're just going to do is factor whatever we can on the top, and we're going to see if something cancels. It looks like we can factor a 5 out of each term on the top. So we're going to do that. When we pull out the 5, we get a plus 3 left. We have a 10 on the bottom. And these two guys will cancel out. And so the 5 and the 10 go away, and a 2 remains in the denominator. So that gives us a plus 3 over 2. And that's our result. All right. So now, what if we have something like this? So for this guy, we don't have a squared term, so we can't factor in like the, the P and Q sense, but it looks like we can factor something out of both the denominator and the numerator. So in the denominator, we have a 6 and a 12 that we're working with. It looks like we could factor a 6 out and be fine, right? Yeah, so we factor a 6 out on top. We're left with an x minus 2. And on the bottom, just like Ed said, we're going to factor a 7 out, and we're going to x minus 2 on the bottom. So this is a good situation because we know we can cancel some stuff, which always makes for a more satisfying result. 6/7. Every once in a while, you will factor stuff out, and it won't cancel. That's not a satisfying result. That sucks. It feels like you just did a bunch of work for nothing. Or sometimes you'll do a massive factorization and then 2 little factors will cancel. That's also not, that's not really satisfying, but that's okay. Not everything has to be satisfying for it to be good. All right. Sorry, what was that?
6 factory 6.
Oh, okay. All right, you already had it. Okay, cool. So once again, we're going to play the same game that we just played on the upper example here. We're going to see if we can factor out whatever we can. Just like Ed mentioned, it looks like we can factor out both a 6 and a t from this numerator. So if we factor out a 6t, we end up with 3t plus 1 left. Don't forget this 1 over here, right? Even though we factored out this whole 6t, can't forget that the 1 remains. All right, so on the bottom, what did you want to factor out on the bottom, Ed? Good. 3 and a t, right? If we factor out 3t, then we end up with 2t plus 5 left. All right, so first thing we're going to notice is that these factors don't match, so we can't cancel those. That's kind of a bummer, but that's okay. We'll move on. So we can cancel these t's, and then we can convert the 6 over 3 into 2, which is what it's equal to. So we have 2 times 3t plus 1 over 2t plus 5. And that's it. We can't factor anymore. We can't cancel anymore. So we're done. Sometimes you might be tempted to put this, like multiply this guy back out and put it into like a more traditional polynomial form. There's no need to do that. That's just extra work, right? If I don't ask you to factor or to multiply it back out, don't do it. Leave it as it is. All right. So here's another example. So this one's a little bit different than the ones we've just been doing. The ones we've just been doing, we were factoring out a single factor out of each term. For this one, we'll fully factor this top polynomial, and we'll see, oh, and the bottom, and we'll see if we can cancel any like factors. What does this top one factor into? Very good. X plus 1 and x plus 2, because 1 times 2 is equal to 2 here, and 1 plus 2 is equal to 3 here. That's how we know that works. For this bottom, it looks to me like we might have a special product here. Does anybody remember what the special product is? A squared minus b squared. What does this equal? Good. A plus b times a minus b. All right, and so for this particular one, a is x, b is 1, and so we have x plus 1, x minus 1. We have matching factors, so we'll cancel those. Oops, no, that was the right one. So we'll cancel the x plus 1s out, and then we just write in what's remaining, x plus 2 over x minus 1. All right, so I have a little cautionary thing here. It's really common for us to go through and try and cancel things when we're not allowed to, because it feels good to cancel things. I understand that feeling, but you got to resist that, right? You got to do it in the way that's proper. So you have to factor everything out until there's only multiplication separating each term, and then and only then are you allowed to cancel. Right? A lot of times people want to do this and they want to say, well, there's a 5 in the denominator and there's 1 5 here. They just both cancel out and this equals a squared. That's not the case, right? You got to make sure you fully factor this stuff out. Then and only then are you allowed to cancel factors. Okay. So let's do another example. So this is another one where we're going to have to factor out fully the numerator and the denominator. So let's go about doing that. So one thing we'll notice, 3 is prime. There's not a whole lot of factors to -1, so I'm just going to write this out and see if I can find the correct configuration. Whoops. All right, so I got 3x and an x. I only have -1 as the factor, so it's 1 and -1. That's what goes in here. I just need to figure out which one goes where. If I put a -1, if I put a -1 here, then I'm going to end up with, and a +1 over here. We can already see that when I multiply the 3 by the +1, I'm going to get a +3, and that's not good, because I wanted a -2 in the middle. So I'm going to swap these around real quick. It's clearly not that configuration. -1, +1, right? You guys can check if you want to see if that works. I'm pretty sure it does, because when we have 3 times the +1, oops, did I do that backwards? I think I did. Sorry about that. So it should be a +1 here and a -1 here. There we go. Because when we do 3 times the -1, then we get -3x, and if we add 1x on top of that, that'll give us this -2 middle term. Okay, so with the bottom, let's see what it factors out to. Just a helpful little hint, you know, they want these problems to be satisfying for you guys. So if you're having trouble finding how the bottom factors, sort of look at the top factors and consider those and see if it maybe factors into one of those, because they want these to cancel for you. They want them to work out nicely. So for this one, this is x minus 2 and x minus 1. Minus 2 and minus 1, when we multiply them together, they give us this positive 2. And when we take the sum, they give us a negative 3. So we know those work. All right. Now all we need to do is cancel like factors. We have an x minus 1 on the top and the bottom. And then we write what's left. And there we are. So once again, take a look at the denominator and the numerator, factor fully, cancel. All right, sometimes it's helpful to factor out a negative 1. We've seen this done before, just not with factoring. So for this one here, we would notice that this polynomial on top is prime, so we just leave it be. But this one, we could factor a 2 out to start off with. So we have x minus 4. A 2 is factored out, which leaves us with a 4 minus x. And we'll notice real quick that x minus 4 is the opposite of 4 minus x. So all we do is we factor out an extra negative. We put a negative out front, x minus 4, and then we have 2 times x minus 4 on the bottom. We have like factors, so we get to cancel those, and then we get a negative 1/2 remaining. All right, so if it looks like you can almost factor out, but it's not exactly matching, think about what would happen if you reverse the signs. If that works, factor a negative out. All right, so that is section 1, just on the introduction to rational expressions. Now we're going to go through all the operations on rational expressions. You guys should recognize this routine by now. We're going to go through multiplication, then division, any particular rules associated with each one of those. Then we're going to go over addition, subtraction, yada yada, and then we'll move on. So for today, we'll just go over 6.2, which is multiplication and division. Now, if you remember your rules for multiplication and division of fractions, they're the same for the rules for rational expressions, because fractions really are just rational expressions, right? So this guy, the product of 2 rational expressions, to multiply rational expressions, form the product of the numerators and the product of the denominators. So we multiply straight across the top and straight across the bottom, just like with regular fractions. All right, so let's do some examples of this. So these examples say multiply and simplify. Just remember in this class, even when I don't say it, always fully simplify. Sometimes I might forget to write that, but you know, I've said it now in class, so always fully simplify. Don't give me something that we can cancel in the end. All right. So for this guy, we use our rule of multiplication, which says we multiply straight across. So this is 3 times 5a cubed over 4 times 5a. The 5's will cancel. One of the a's will cancel. And the 3 and the 4 looks like those remain. So we'll have 3/4 a squared. All right. Now we have something like this. So when I see this guy, I say, I don't want to multiply that. I'm guessing you guys feel the same thing. So what we're going to do is, before we start all our crazy multiplication, we're going to factor all these polynomials out, and we're going to see if we can cancel anything. Otherwise, we would have to multiply this entire polynomial by this x plus 4. Then we'd factor everything and try and cancel. We don't want to do that, so we're going to do it beforehand. All right, so we're going to have one big fraction. And so remember, this is just this polynomial over 1 is what we're really saying here. So we're going to multiply straight across the top, straight across the bottom. First things first, we're going to leave the factor that was already in the top way over here on the side. Second thing, we're going to factor this guy. All right, so we have an x squared out front, so we know that we have just plain old x's. We've got a negative 10 back here where c is, and then we have a negative 3 up front. So what two factors of 10 differ by 3? Obviously, 5 and 2, right? So we have a negative 3, which means the negative sign goes on the larger factor. All right, so now we have 3 factors on the top. Let's factor this bottom one and see if there are any commons. So with this bottom guy, I think you'll notice pretty quick that 2 factors that multiply to equal 25 and that when added they equal negative 10, that's negative 5, right? Negative 5 times negative 5 is positive 25. Negative 5 plus negative 5 is negative 10. So that's x minus 5 twice. Now we can cancel some things. We can cancel one set of the x minus 5s. One set has to remain because there's nothing to cancel with it on top. And then we just rewrite our problem. There we go. And remember, you might be tempted to multiply this stuff out. Don't do it. You're just wasting your time. I'm not going to ding you points if you do that, but I don't know. You could do it for fun if you wanted to, but you don't have to. Okay. So for this example, once again, we have one of these guys where we could go about multiplying all this stuff together and then refactoring it all out. But since it's already sort of factored in its own way, we're just going to break down each one of these little sections into its factors. All right. And draw one big division line. So I'll factor this guy first, 10x plus 20. So it looks like we can factor a 10 out of that, right? So we have 10 times x plus 2. That can't be factored anymore. So now I'm going to factor this side. Once again, this is a squared minus b squared, right? This is the special product. So we already know what this equals. This is x plus 1, x minus 1. All right, so now we're done factoring out the top polynomials. Now let's factor this guy out. So this guy is clearly going to factor into something looking like 2x and x, right? The coefficient's prime, so we don't need to consider any other options. We have a positive 1 here and a negative 3 in the middle, right? So we either have two positive ones or 2 negative ones. Clearly the middle is negative 3, so it's 2 negative ones. Yeah, and so when I was asking if you guys have a handle on factoring, like this is it, right? Like we're factoring multiple times in one problem here. So yeah, if you're not clear on factoring, keep practicing. Okay, last thing. Well, not last thing. Last thing in this step anyway. We're going to factor this last denominator out, 5x plus 10. It looks like we can factor a 5 out of that. So we have a 5 in here in the middle of all this stuff, and then we have an x plus 2. All right, now let's go through and see if we can cancel anything. So we know that we can cancel the x minus 1, the x plus 2. There's no other polynomial factors, but we do have a 10 over a 5, which is actually equal to 2. So we're going to remember that when we write our next step. So 10 over 5, that equals 2. And then we have x plus 1 left on the top, and a 2x minus 1 on the bottom. And that's it. All right. And so, you know, like these might look like they're a little unwieldy at first, but you know, as you can see, I took that one and said, well, I'm going to factor this first polynomial, factor the second polynomial, just take it step by step and break it off bit by bit, and eventually you'll get to the spot where you can cancel a bunch of stuff. All right, division. The quotient of two rational expressions. So just like fractions, right? If you have a over b divided by c over d, you just flip that c over d and multiply by the reciprocal straight across. So if we had 2/3 divided by 1/6, we would say actually that is 2/3 multiplied by 6 over 1. All right, so it's the same thing when we deal with polynomials. For example, let's do this first division here. So all we need to do is follow our rule, which says we flip this fraction and then multiply. So the x over 5 stays the same. The 7 over y flips to y over 7. Then we get xy over 35. All right, so for this example number 2, we just remember x plus 2 is actually over 1. And so we take this second fraction, we're going to flip it and multiply. So this is equal to x plus 2 over 1 times x plus 3 over x minus 1. We remember to leave our parentheses in there so that things don't get jumbled up. So remember that those things go together. Okay, so now I don't see any common factors, so we're just going to leave it as is. This is x plus 2 times x plus 3, and that's over x minus 1. All right. Here's another example. Once again, just the same as fractions. We're going to take this guy and we're going to flip it and multiply. All right, so yeah, so I'm going to say x squared minus 2x minus 3 over x squared minus 4 times x plus 5 over x plus 1. So I just flipped these two guys. Now, on our next step, I'm going to go ahead and factor each and every polynomial, and then we'll see if we can cancel. So we'll deal with this guy first. This polynomial is going to split up into, we have a -3, so we're looking for two numbers that multiply to equal to a -3. When they sum, they equal a -2. Well, the only factors of 3 are 1 and 3, so it's either -1, 3 or +1, -3. Since the middle term is negative, the 3 has to be negative. And then this guy doesn't factor anymore. Then we can factor this bottom out. What does this guy factor to? X squared minus 4. There you go. X plus 2, x minus 2. That's because that's a special product. A squared minus b squared is equal to a plus b times a minus b. Okay, and then this last factor over here, x plus 1, that guy just stays the same. Now we go through and cancel any commons. So we have x plus 1 is a common, and really nothing else. See, that's a result that's not that satisfying. But it's correct, so it's good. Okay, so now we just write out what remains. X minus 3, x plus 5, And on the bottom, we have x plus 2 and x minus 2. All right. I think we have some more. Yeah. Okay, so once again, when we have a solo polynomial like this, we always consider it to be over 1. Since that's in the denominator, we are going to flip it. So we're going to rewrite this as a squared plus 3a plus 2 over a squared plus 4. And this is multiplied by 1 over this polynomial, 5a squared plus 10a. Okay, so now I'm going to factor each one of these polynomials and see if stuff cancels. This first one here, I think we've already done this one a couple times today. So this one splits into a plus 2 and a plus 1. Right, the 1 just remains. When we go to split up this guy, we're going to notice that it's a square plus a constant. That means it's prime. If it's a square minus a constant, then you can factor it. But if it's a square plus a constant, it's just prime. So we're going to leave that guy. Then we're going to see if we can factor this one out. So it looks like we can factor a 5 and an a out of that guy. So we have 5a, and what we have left will be a plus 2. All right? Yeah, so the only thing, in fact, the only thing that cancels is the a plus 2, and all the rest just remains. Once again, sort of an unsatisfying result. And when I say unsatisfying, I just mean that's for me personally. Personally, I really love it when you have something really complicated and then it all just goes away. Like you cancel everything but one variable, and like you started with like just this mess of crap that you were just dreading, but all of a sudden it all goes away. All right. So that was, man, that was a super fast lecture. So that was the lecture on multiplication and division. Once again, like, you know, you just remember these rules. It's the same rules for fractions. Any questions? No. Well, I guess go enjoy the sunshine then. See if you can catch that World Series game. Right? If they knew it was going to be so short, they might have just showed up anyway. I was thinking that, yeah, I still haven't perfected the timing on these.